As you can see from the title of this video, this tutorial is about writing electron configurations. We're just coming off of a section in the chapter where we've learned that electrons are not contained in set patterns like some of our old models show, in paths around the nucleus as we thought in the Bohr model. But we found out that they are contained in specific energy levels, but they're contained not in orbits, but specific orbitals, which is a three-dimensional area where it's most likely to find an electron. Electron configurations are an address, so to speak, for finding an electron. It gives you a very good idea about the probable location of an electron and what type and of what energy level orbital it's in. If we're going to discuss electron configurations, we have to talk about where they come from. And that introduces two ideas that are called the Aufbau Principle and the diagonal rule. The Aufbau principle explains to us how these orbitals get filled. And the definition of the Aufbau principle says that electrons always fill the lowest energy orbital available to it. Electrons very often, I say, behave like high school kids in the morning. You want to expend the least amount of energy because the more energy they have, the more unstable they become. Electrons want to be stable, they want to be in relaxed states, in ground states. So the Aufbau principle says electrons fill the lowest energy orbital available. As we learned when we were learning about the Bohr model and we looked at our rings of energy levels, first ring, first energy level, second ring, second energy level, they get progressively farther away. As you get farther from the nucleus, the energy goes up. So the idea is that most often you will see a numeric increase in the energy level when we fill them. However, there are some exceptions due to complexities of orbitals. We learned that there's an S, a P, a D, and an F. And if you remember from the shapes that we drew in class, S orbitals are spheres, very simple to make. P orbitals are dumbbell, still relatively easy. D's are flower-shaped, right, or double dumbbelled, and they're starting to get more difficult, and F's are flower-shaped, they're the most difficult. So, if we had a way of ordering the levels from lowest to highest, it would make writing configurations easy. And that is what the diagonal rule is called. Here is how the diagonal rule works. If you're going to write this on a piece of paper, start at the top by writing 1s. Going straight down from there, list all the other s orbitals. 2s, 3s, 4s, 5s, 6s, 7s. 7 energy levels, each one has a s orbital in it. There are the s orbitals. Then you'll list your p's. We don't see a p orbital till the second energy level. So 2p, 3p, 4p, 5p, 6p, 7p. Then draw your d orbitals. 3d, 4d, 5d, 6d, 7d, and lastly your f orbitals. 4f, 5f, 6f, 7f. Now, there is such a thing as a g orbital. They believe it to exist. It's even higher in energy than an f orbital and even more complex. But the catch is this: we have yet to synthesize an element or discover an element that would require a g orbital to be filled to write its stable state electron configuration. So we're not going to worry about g orbitals. The reason they call this the diagonal rule is because if you fill these diagonally, right, you will get the order that orbitals are supposed to fill in. Always start at the top right. First orbital to fill is a 1s. Once you get to the end of the arrow, go to the top of the next one. Then a 2s fills. Then a 2p followed by the 3s fills. Then the 3p followed by the 4s fills. Then the 3d, 4p, 5s fills. 4d, 5p, 6s. 4f, 5d, 6p, 7s. 5f, 6d, 7p, 6f, 7d, and lastly, the 7f. Notice we are filling these diagonally, hence the name diagonal rule. And a couple highlights that I want you to see. Notice there are a few exceptions where they don't fill numerically. For instance, according to the diagonal rule, after the 3p fills, the 3d does not. The 4s fills. Then we go back and fill the 3d. The reason for that is this: an s orbital is so easy for an atom to create, even though it will do so in a higher energy level, which usually has more energy. The d orbital is so complex that even in a lower energy level, it requires so much energy to make that it makes this orbital more energetic than this one. So the 4s fills before the 3d. Notice 4p, 5s fills before the 4d or the 4f. But if you follow things diagonally, you will be able to write electron configurations. So we'll leave that there to refer to it, but make sure you're able to draw it because you won't have that for your test. And we're going to take a look at some examples. First example, let's take a look at something like phosphorus. In fact, slide this guy over here. If I'm going to write an electron configuration for phosphorus, the first thing I need to do is figure out how many electrons do I need addresses for. Looking at the periodic table, phosphorus has an atomic number of 15, which means we need addresses for 15 electrons. Then what we're going to do is we are going to fill orbitals in the order that we see them here, placing the maximum number of electrons that that type of orbital can hold until it's filled, and then continue until we've had 15 electrons. So, according to the diagonal rule, the first orbital that fills is a 1s orbital. If you remember from what we learned about earlier, an s orbital is able to hold 2 electrons. So we say 1s, 2. And the number of electrons in the orbital, always goes as a superscript or an exponent from math class. After the 1s fills, a 2s orbital fills. Again, an s orbital can hold 2 electrons. So right now, we have written addresses for 2, 4 electrons. We need 15, so we have to keep going. After the 2s fills, we jump back up, a 2p fills. A p orbital is able to hold 6 electrons. So 2p, 6 is what will fill there. 2, 4, 6, all right? So 2, 4, and then 6 more means we're at 10 electrons. We need 15, we keep going. After the 2p fills, the 3s fills. And again, an s can hold 2 electrons. So 2, 4, 10, 12, we need to keep going. After the 3s fills, we jump up, we fill the 3p. Now, a p orbital can hold 6 electrons. But if we do that, watch what happens. 2, 4, 10, 12, 18, we've surpassed the number of electrons that phosphorus has. The last orbital that you write is allowed to contain less than the maximum number that that type can hold. So S has to be 2, has to be 2, has to be 6, but because the P, right, only needs 3 more electrons, we will only put 3 electrons in that orbital. And the only orbital that can be partially filled is the last of the type. It can be an S, a P, a D, or an F, but it has to be the last one. And notice the numbers add up. 2, 4, 10, 12, 15. So you have 2 electrons in the 1s orbital, 2 in the 2s, 6 different electrons all in the 2p, 2 electrons in the 3s, and 3 electrons in the 3p. Taking a look at another example, let's look at something like silver. Silver symbol's Ag. Right? Ag contains 47 electrons. So we need to write addresses for 47 different electrons. We will try to fill the same way that we did before. The first orbital that fills is a 1s. An S can hold 2. The next orbital that fills, 2s. It can hold 2. After that, jump up, 2p. A p can hold 6. After the 2p, the 3s. Again, an s can hold 2. After the 3s, the 3p, and a p can hold 6. And it is holding all 6. It's only a 3 here because that got us to 15. We were at 2, 4, 10, 12. We need all 6. We're nowhere near 47 yet. After the 3p fills, a 4s fills. It can hold 2. After the 4s, you jump back up. It's the 3d. A d orbital can hold 10 electrons. So stop and take a look where we are. 2, 4, 10, 12, 18, 20, 30, still have 17 to go. After the 3d, the 4p orbital fills. Right? And a p orbital can hold 6. Then the 5s, and an s orbital can hold 2. Right? So we were at 30 here, 36, 38. Still have to keep going. Right? We still need 9 more electrons. After the 5s fills, it's a 4d. A d can hold 10 electrons. Right? And even though it holds 10 electrons, right, we don't need it to hold all 10. We are going to have it hold 9. Right? Because right, the d orbital right, will get us too far past our 47. Now, for the purposes of Gen Chem, we will always follow this pattern. Right? You are going to find out there are a few exceptions to the filling of orbitals directly, and it has to do with stabilizing whole orbitals. Right? So if you look into the back of your book, you may see some exceptions to this where, for instance, silver probably says 5s1 4d10. Right? We will use this pattern. Follow it directly. I would rather you learn the 89 elements that are normal, and then worry about the other 11 later than worry about the exceptions to start. So we're going to follow the set pattern. Last but not least, let's try something like calcium. Okay. Calcium has 20 electrons. So we do the same thing that we were doing before. Okay. Start filling. The 1s is first. An s can hold 2. After the 1s fills, the 2s will fill. An s can hold 2. After the 2s fills, a 2p fills. It can hold 6. So we have 2p6. After the p fills, it's the 3s. 3s2. Periodically take a look, 2, 4, 10, 12, still have 8 to go. After the 3s fills, the 3p fills, and a p can hold 6. That takes us to 2, 4, 10, 12, 18. And lastly, a 4s, which can hold 2. Do we need it to hold 2? This time we do. So there are 2 electrons in the s orbital for calcium. So if you learn your diagonal rule and you simply follow that pattern, you should be able to get yourself through any examples and homework that we may have. Last thing that we didn't mention, we just didn't happen to do an example like this, an f orbital, right, holds 14 electrons. So make sure that if you run into an f orbital, the maximum number it can hold is 14. Right? For instance, the 4f that would fill after a 6s would be 4f14 for what's going on. If you're having any trouble with any of this, please feel free to stop in for some help. Other than that, hopefully this straightened out any problems that you may have been having.